He's working as a senior research scientist at Honeywell, Bangalore since 2019. He obtained his doctoral degree in process systems engineering and data sciences from IIT Madras. He obtained his bachelor's degree in electronics instrumentation and control engineering from Sri Venkateswara University, Tirupati, and his master's degree in digital systems from JNTU Anantapur. His research interests span the fields of causality analysis, process identification, subspace systems identification, process control, process data analytics, and time series modeling and analysis. Sir, we are eager to listen to your talk. Just get started your presentation.
Yeah. Thank you, Professor, for the introduction. I hope I am audible.
Yes, sir, you are right.
Yeah. Thank you for the confirmation. Yeah. Hello, everyone. Good evening. This talk is about machine learning applications in advanced process control. In industrial plants such as refineries, petrochemicals, metals, and minings, etc., achieving optimal performance and efficiency requires an advanced process control, optimization, and monitoring solutions. So the most commonly used control and optimization solutions even today typically are PID, proportional integral derivative control, and the model-based control, that is more model predictive control, MPC, we call it as simply, which rely on dynamic models of underlying plant. Therefore, models play a key role in implementing advanced process control solutions in process industries. So in this talk or in this session, I will briefly present different types of models used in implementing advanced control solutions in process industries. The outline of the talk is as follows. First, I will introduce 3 different use cases of models. Then I talk about identification, where we will see the identification of 3 different models. And finally, I talk about the machine learning and deep learning based modeling techniques, focusing on, especially focusing on inferential applications in advanced process control. Now, there are...
அதை ரெக்டிஃபை பண்ணிட்டேன் சார். அது இப்போ பழைய வருஷத்துல எல்லாமே இருந்தது, புது வருஷத்துல இப்படி மிஸ் ஆச்சுன்னு தெரியல. ஸோ
Sorry?
That was a glitch.
Yeah, okay.
Please continue.
Yeah, okay. So there are some of ML applications we recently adapted in process industries. We expect the ML algorithms to be provide more accurate predictions, better process optimization, and the ability to handle complex nonlinear processes. The major applications in process industries that we adapted recently are process optimization and quality control to identify optimal operating conditions and predict the product quality early so that the operator engineer can take an appropriate actions. And the soft sensors, which are also known as inferential models, to estimate the difficult to measure process quality variables. So in process industries, always we cannot measure all the process quality and properties using physical sensors. So we may need to use the inferential or soft sensor or virtual sensors to measure those process quality variables. And the other application is predictive maintenance, especially to analyze historical data and real-time data and predict the equipment failures before occurring the failures to take a preventive action. And also the other application is faults and anomalies detection to assist in diagnosing issues and detecting operational deviations, if any, during the plant operation. And if you talk about advanced process control, there are numerous benefits of implementing control and optimization solutions in process industries, including the significant cost savings. So advanced process control solutions enhance operational efficiency and reduce energy usage and maximize profitability and provide the safe operations. So these factors and also the key value drivers motivate process industries to adapt to APC solutions in their plants. The most common control strategy even today used in industries is the proportional integral derivative control, which is a feedback single variable control. The output from the control, the PID controller, is a weighted sum of 3 factors. One is the error signal, which is typically the difference between the set point and the process variable, that is the difference SP minus PV, and the integration of an error and a derivative or the rate of change of an error. For example, consider a tank system with a liquid. The objective is to maintain the temperature of the liquid at a particular value, which is typically known as the set point or the SP. The PID controller here continuously reads, this is the PID controller, the temperature PID controller. It continuously reads the output of the temperature, the output temperature of the liquid, and collects the error or calculates the error between, the error is in the sense the SP minus PV, and generates a control signal, which is output from the controller. In industry, we use the notation as OP. It generates this OP accordingly to maintain the temperature at the desired level. The key step here is adjusting the weights or tuning the PID parameters. The weights are nothing but the PID parameters according to these process conditions. So there are different tuning methods based on process parameters. The typical process parameters are gain, time constant, and delay. So to adjust these weights or to tune these PID parameters, one has to understand the process behavior, the process dynamic behavior, which needs to be captured in terms of three parameters: the gain, time constant, and delay. So the expression or the mathematical equation that relates these three parameters, we call it as a process model. So in order to tune the PID parameters or the weights of the PID controller, so it is necessary to identify the process parameters. That means it is necessary to identify the process model. So with the help of the model, we need to capture the process dynamics. So once we get the process dynamics and the process model with the help of gain, time constant, and delay, there are different methods to adjust these weights. Although the PID controller here is the most commonly used control strategy, it has few limitations. If you have a process here and if you step the input some value, so the process will not start respond immediately. It will respond after some time. So that means the process may have some delay. If you talk about process industries, for example, in oil and gas at refineries, you have larger pipes that connect the columns. So typically the delay could be in terms of in minutes. It can go to some hours, some 60 minutes or 2 hours, sometimes 120 minutes if it's a larger pipe with connecting the column. So with the PID controller, it is difficult to tune the PID parameter for the process with large time delays, or we generally call it as dead times. And the other limitation of PID controller is difficult to handle or control the process with inverse response or unusual dynamics. The inverse response is when you step the process, it will start responding in the opposite direction to the normal behavior for some time, and then it starts responding as the actual as per the normal behavior. This is typically the inverse response. So it is difficult to control such kind of processes with a PID controller. And the third limitation of PID controller is it is unable to reject disturbances due to feedback mechanism, as the disturbance is addressed only after the control action is taken. So if you see here, the disturbances is added to the PV after the control action is taken. But ideally, we expect the feed forward kind of disturbance rejection. So before taking the control action, ideally, we expect to account the disturbance so that it will account for the disturbance and reject the disturbances. And the fourth one and the important limitation of PID controller is it is unable to handle interactions where we have many OPs can affect many PVs. When you have multiple control loops, and it is unable to handle constraints as well. So if you take a plant, we may need to minimize certain utility and maximize certain product. So to address these limitations, industries have adopted the MPC based, that is model predictive control based advanced process control strategies, which is typically above the PID control level. The basic 4 elements of MPC are: you need to specify the trajectory, it specifies the reference trajectory, and based on the reference trajectory and based on the model, the dynamic model of the process or the plant, it generates the prediction of the process output. And according to the reference trajectory and predicted process output, and with the given constraints, it tries to provide or compute or generate the optimal movements in the inputs, such that it minimizes the error between the actual and the output, I mean the predicted output. So again, to implement these MPZ-based advanced control solutions, so it is necessary to identify the process dynamic model between the process inputs and outputs. So this is another use case of model in process control, which is typically in the form of MIMO, I mean multi-input, multiple output model. So here we're talking about dynamic models. So the MPC and the PID controllers are both completely rely on dynamic models. So what is a dynamic model? How do we incorporate it? So in a process variable whose behavior changes over time is called the typical dynamic behavior of a process, and we need to model such kind of behavior. So we call that kind of modeling is a dynamic modeling. So here, how to incorporate the dynamics? For example, let's consider the inputs here. We have inputs 1 to U1 to UM, and the output is Y. For example, if we consider only one output and multiple inputs case. So this is a typical mathematical model that represents inputs and outputs in a static manner. So here, if you see the expression, there is no time factor here. So whereas dynamics means we need to bring the time factor. So the behavior of the process over that time. So there are two ways we can incorporate or we can bring the time factor in the mathematical model. I mean, we can incorporate the dynamics. One, dynamics in the input variables. So generally the output is kind of depends on the past inputs. So the past input in the sense you need to bring the lag terms of the inputs. So where U1, it runs from K minus 0 to P according to the process order. Similarly, U2, second input. Similarly, the nth input. So this is how we can bring the dynamics in the inputs. So what is the effect of your output over the changes in the input over the particular period, starting from now. So you're standing at now, you can apply the last 1 hour, 2 hours, 3 hours, depending on your process conditions. So that much past you have to go back and apply and see the effect of the past inputs on our output. That is how we capture the dynamics due to the input changes. The other way of incorporating the dynamics is with the output variables as well, in addition to the inputs. So again, to bring the dynamics, we need to bring the past terms of or the lag terms of output variables. So here the parameters P is the model order. Generally, we need to identify depending on the process conditions or using some criteria. And M is the number of inputs here. So this is how we can bring the dynamics of the process into the model structure we are going to identify for the control and optimization. So we have seen the two use cases of models so far, and the third use case is measuring the process quality variables. So as I mentioned, one of the application of machine learning algorithms we recently adapted, that is a sensor inferential model. So in a typical process industries, to implement any control and optimization solutions, it is required to continuously measure the key process quality variables and properties, which are generally not possible to measure with physical sensors. For example, if you take the kerosene sulfur or product recovery or gas oil density or reed vapor pressure, etc., these are typical process quality variables and properties. So these kind of process variables we can't measure continuously, that too according to the controller frequency. So the typically controller frequency could be 1 minute or 30 seconds depending on the process conditions. But according to the controller frequency, it's not possible to measure these kind of. So the generic approach in typical industries, the engineer collects the available measurements of the particular variables which are related to the particular process quality or property variable, and try to bring some kind of mathematical relation and get that process quality or property variable. That generally we call it as lab data. And the process that engineer goes through to get is lab analysis. So that data point for the process quality variable or property variable, typically we get 1 or 2 data points per week. I mean, the sampling rate is very slow. But if you get 2 data points per week, but the controller is running at the frequency of 1 minute or 30 seconds. So to take an appropriate action for this process quality or property variable, it is required to get the data point according to that frequency. So that's where we use a kind of models that we call it as inferential or a soft sensor model to continuously measure the key process quality variables and properties according to the controller frequencies. So to summarize, 3 types of models are required to implement the advanced process control and optimization solutions in process industries. One, the models, which is generally in dynamic form, and CISO, single input, single output for PID tuning, for tuning PID parameters. And the second use case is models, which are again in dynamic form, especially in a MIMO structure, for implementing the implicit based advanced control and optimization solutions. And the third use case is models, which can be either static or dynamic. If we talk about the inferentials, sometimes the quality or property variables do not change with respect to the time. So for certain cases, static model is sufficient. For certain cases, we may require to incorporate dynamics to capture the dynamics so that you get the better accuracy of the model predictions. So the third use case is models either in static or dynamic form, and specifically in meso structure. This is for measuring process quality variables and properties, which we are calling it as soft sensors or inferentials. So there are three kinds of different models. So how to identify these models? There are 2 approaches. One is the first principles approach, which uses physical laws and conservation equations. To build these first principle models, we require a good understanding of the physics of the process, which is rarely available for large class of processes. Whereas the second and alternative approach is the data-driven approach, which uses experimental data. So we perform experiments, collects the data, and selects a model structure and estimate the parameters and try to capture the dynamics of the process with that model structure. Identifying process models from measured data is a
I have one
natural
question, Sudha,
alternative.
here.
Yeah.
Can we integrate both these two
Yes,
single model?
Yes, correct. We can integrate. If you have some knowledge about the process, right? If you have some prior knowledge about the process, you can bring that
what I
knowledge
meant is
into
we can build the physics-based mathematical models and also the experimental data. Both we can feed to the model, machine learning models.
both together. I mean, it depends on how you are going to use that. One is, if you know some information about the process, you can bring that information into the model structure you are building from the data. So that means you know partial amount of the process, remaining a portion you are estimating from the data.
Okay.
Okay.
So it is
the
it
thing
is
you are
possible
calling,
to
right,
train a machine learning model based on experimental data as well as first principles equations, right?
So typically the first principles is very limited because we may not have good knowledge about the process in many cases. If you talk about industries, right, there are huge plants. You may not have the complete idea. Even if you know the complete idea, if you bring some kind of model, mostly you can use that model for simulation and understand the process characteristics. When it comes to the real plant, when you implement the control and optimization solutions, we mostly prefer the data-driven models because if you build the first principle models, it's kind of you are building from the process knowledge, but you are not considering the process behavior during the plant operation.
Okay.
The operating conditions keep on change. It's not fixed. So you need to accommodate those changes in our model structure. That's possible only with the data-driven.
One hurdle I found using ML models in the chemical process is the quantity of data. The data is not huge, right? When it compares to the, let's take general corporate data about the product or the anything, they have millions of data sets. The quality of machine learning, the models are very good if you have so much of data. But when it comes to the process, now we'll have limited amount of data, right? How to handle this?
Yeah. So there are certain things, right? Whatever we have observed, right? If you really need complex model structure for your application, then only we will turn to the advanced machine learning and deep learning kind of models. So it's not like one model structure generally we give for the user, for the customer to try that model use directly. So generally we give different kind of models and different kinds of algorithms. So we do not know because we are kind of giving the generalized solutions, right? If you are giving customized solution, you can take the data from the customer and analyze offline and do some kind of pre-processing and try different thing, and whatever you get the better model that you can deploy for the customer side. But when you provide like one kind of a solution for the generic solution for some number of customers, right? Generally, we give as a option for the user to choose different algorithm and different model structure. So that list has from basic algorithms to the advanced machine learning and deep learning algorithms. If you generally, mostly the operator and engineer may have some idea about the process. With his idea, he thinks that if the data is very limited and if he knows that the relations could be linear, then mostly he prefers the linear based algorithms.
Okay.
Yeah, if he has sufficient amount of data and if he thinks that there could be some complex nonlinearity that needs to be captured to get a better predictions, then really he turn to the advanced algorithms. If the operator engineer doesn't know anything, then he try all the methods, and we generally for all the methods generally we provide some kind of quality metrics, and based on metrics, based on he will check the predictions on the new data and all. So he pick the whichever data is doing good.
Okay. Thank you.
Okay. So generally, the bringing the known knowledge, right? That's what even the physics informed machine learning models we call, right, in the literature, or people generally talk about. So there, the main thing is to bring the known process knowledge into the model structure, so that whatever you know, you are trying to accommodate in the model structure, so that with the limited or available quality amount of the data, you try to capture the remaining unavailable portion. That is the motivation physics informed machine learning models. Okay, so the widely used and the commonly used approach is the data driven approach. So the identification problem in data driven approach is as follows. So we have the process, we exert the process by stepping the inputs. This is a typical process in the industries. Then we measure the outputs. The inputs, we call it as manipulated variables, so represented with MVs, and the outputs we call it as control variables, so represented with CV. So from this input and output data, we need to identify what are known as step response models. So if you see here, this is the step response model generally we use in industries. However, it is difficult to obtain these good step response models directly from the input and output data due to different reasons, noise, unmeasured disturbances, and the process may be running in closed loop. So due to those reasons, we can't exactly get the accurate step response models. So therefore, we first identify from the data, we first identify what are known as generic form of higher order models. Could be in any form. And then we bring that generic form to a specific form reduced order models, since we use the lower order models for the control. So you can use any generic higher order model form to capture the dynamics as much accurate as possible from the available data. And then we approximate that higher order models to bring it to a specific form of reduced order models. So what are the typical model structure generally we use for this generic form of higher order model identification? The model structures that commonly used for building higher order models are the transfer function form and the state space form models. So this is the general description of transfer function form models, especially in polynomial form, where y is the output of the process and u is the input and ek is the noise. So here b by f, or in the polynomial, if you take this transfer function, this is the plant model, and this c by d again in polynomial form, in a ratio of polynomial form, again this is a disturbance model. If you observe here, a This captures the dynamics common to the both plant and disturbance models. So depending on the polynomial values you assign for this A, B, C, D, F, I mean A, B, C, D, F. So you arrive a different standard model structure that we use in process industries. So these are the model structures. The FIR, a finite impulse response model structure. If you keep these things as ones, and we need to identify only the B polynomial because you know all remaining four, all are one. You just need to identify B. So you get it, what is known as a finite impulse response model. That is one of the widely used model structure in the industries that give you better results when the data is from the open loop conditions. And the ARCS model structure, autoregressive with exogenous inputs. So these three are one. You need to identify only the B by F, these two polynomials from the data. And similarly, the RMAX and OE, it is output error model structure and box sequence. So if you see all these five standard model structures, right, the FIR, ARCS, these two are widely used model structures in industries. Since these model structure, if you write the predictor for these model structures, right, they are linear in terms of unknowns. So you can use least squares algorithm to identify these parameters, these FIR and ARCS model parameters, and it takes less time. In industries, the typical expectation from the users, right, the algorithm should take lesser time and give a better results. Whereas RMAX and OE BJ, if we talk, right, these are nonlinear model structures. You need to use a nonlinear optimization algorithms to identify these model structures. And also the accuracy of model parameters and the model quality depends on our initial guess. And since the nonlinear optimization, it goes through a different number of, some number of iterations, it takes a longer time. So in typical industries, right, if you want to implement for certain larger process, the advanced process control solution, sometimes for if you consider some unit, we implement APC solution per unit. Per unit may have 100 MVs, 100 CVs. 100 inputs, 100 outputs. So to identify such a large dimensional model, it takes longer time if you use RMAX, OE, BJ kind of model structure. Sometimes it may takes 1 week, 2 weeks also to produce the models. So generally, in the industries, mostly the users prefers a less computational. It should take less computational time and provide a better results for the from the data. The other model structure that is also widely used in process industry these days is a state space model structure. This is the general state space model form. You have the inputs U and output Y. You see the another variable here, that X, that we call it as intermediate variable or state, which are generally hidden in the process. For example, if you take a simple liquid level, right, this is the flow rate, input flow rate and output flow rate. These two are measured. If you consider the rate of change of volume, dV by dt, this is generally we don't measure. That is the state of this liquid level system. So which is generally hidden variable. If any state, if you are observing or if you are measuring, that becomes an output. So these are the matrices. Many might know, like state, input, output, direct feed through matrices. So here the objective is we need to identify the matrices, state space matrices A, B, C, D, that captures your process dynamics. So here, although we identify the state space model form, if you talk about the user perspective, right, typically the engineers are compatible with interpreting the models in transfer function form. So although we use the state space model structure internally, again, we need to bring it back to the transfer function form. So you can use the mathematical relation that gives the relationship between your transfer function form and state space matrices to get the transfer function model. And once you get the transfer function model, then that we generally be show to the user to interpret. So these are the two model structures. Again, in the transfer function form, we have another second category of different model structures. So before proceeding with identifying these model structures, we'll see what are the possible issues typically we encounter with industrial data. So these are the possible issues with the industrial data. We need to handle these kind of issues before proceeding with the identification of the model. So oversampling, if the data is sampled faster than needed during the step test, generally the operator engineer does the step test. If it is sampled faster than the needed, right, then the faster sampling leads to the larger data length. So which increases the computational time during the identification. And the offsets and different engineering units. So offsets are nothing but the non-zero means, and and identification algorithms are sensitive to the non-zero means and the units. So we need to handle such things as well. And drifts and trains and disturbances, all these affects the model accuracy. And unmeasured disturbances. And disturbances can be non-stationary, some kind of random walk of behavior. So we need to handle such things as well. This is with respect to the data. If you consider with respect to the process, you may have large and different input-output delays. That is dead time. Or you can have integrating type dynamics. So all these issues we need to handle. Otherwise, it can affect the efficacy of any identification algorithm we use to identify the model structures that we just gone through it. So to handle this, we need a suitable data preparation before the identification. So the issue of oversampling, generally we handle through the data resampling. That is, sampling rate generally we decrease by user specified integer factor, sorry. And data slicing takes care of offsets and different engineering units, data scaling. And drifts, trends, and low frequency disturbances and other unmeasured and non-stationary disturbances, generally we remove using an appropriate free filter. So we apply some appropriate free filter and remove that portion, then we proceed with the modeling. Similarly, the special dynamics, the large and input delays, we estimate the delays between input and outputs, and we remove those delays as part of the pre-processing. Then we do the identification. And then integrating type dynamics, we difference the integrated type outputs. Once you difference that, it becomes a self-regulating a stable CVs. Then do the model identification and add a pure integrator as post-step. So with this, we'll proceed with the identification of ARCS models. So this is the typical structure of ARCS model, just we have seen now. So input and the disturbance model, which is a plant model, both added together to get our output. So if we see the autoregressive with extra inputs, this is our input. If we remove this is plain autoregressive model, a typical time series kind of model. So when you have the input, it becomes exogenous. So that's why we are calling it as ARCS model. And we need to identify two polynomials, A and B. So we need to identify two types of parameters. Parameters corresponding to the A polynomial and the parameter corresponding to the B polynomial. And here NA and B are the orders and NK is the delay. So once we identify the delay, then we account and accordingly we form the model structure and identify this model. If you see here, both the plant and noise model share the common dynamics. A is common. Suppose if you make NA as 0, then it reduces an FIR model. So both FIR and ARCS can be identified using least squares approach. If you see here, the predictor, if you write the predictor, if YK, if you write in terms of all lagged variables, you have unknowns. So unknown, it is linear relation in terms of unknowns, so you can use least squares. So the problem formulation here is you have n measurements of input and output data of any unknown process. So we need to identify the orders NA and NB polynomials and the delay. And the orders generally you can use any criteria, the KKR based information criteria. Generally, the practical approach, right? We can't directly derive that order. So we have to try different orders by keeping some maximum order depending on some initial idea. And for every order, you need to evaluate the loss function. So we need to pick the order which gives the minimum loss function. And then we need to identify the coefficients of A and B polynomials and the second order properties of noise. That means variance covariance matrix of your noise. So here if you see, right, as I mentioned, the predictor is unknown in terms of, the linear in terms of unknowns. So if you see for this ARCS model, the unknowns are A1 to AN and B1 to BN. And knowns are, which are also known as regressors, the past terms of both input and output. If it is FIR model, you have only the past terms of inputs. So similarly, you have the parameters B1 to BN. The remaining formulation is same. So if you write the predictor, y hat up to information k minus 1, you're trying to predict what will happen now. So if we talk about here, the B is unknown, U is known. Again, this is unknown, this is known. So it is linear in terms of unknowns. So you can use least squares algorithm to identify the parameters. And we have the unique solution, the analytical solution, the P transpose P inverse, P transpose Y. So using this or using least squares algorithm, you can identify the FIR and ARCS model. So for example, to illustrate this ARCS model behavior, consider the flow control loop. For a typical control, we have three variables, as I mentioned initially. Set point, the control output OP, and the process variable PV. So this is the typical snapshot of the SPOP PV data of a flow control loop. So here we need to identify the model between OP and PV. This is for a PID controller tuning. So each PID controller is a single variable controller. So we need to identify a dynamic CISO form of a dynamic model. So once we identify the ARCS model here, so the original model, the higher order model here we're building is a 10th order, both the 10th order parameters. This is the typical step response of ARCS model, higher order model. As I mentioned, although as an intermediate step, we use higher order generic model structure. At the final, for the end user, we need to bring it to the specific form reducer order model. So here we are doing some kind of we need to do some kind of curve fitting here to approximate this higher order model step response to a reduced order. So you know, right, any higher order process can be approximated with lower order with time delay. So that's where generally we can use two kinds of approximations, mostly widely used ones are first order plus time delay and second order plus time delay. So if we fit the first order plus time delay for this higher order model, and this is the step response, the orange one, which is above the actual higher order model step response. It is exactly capturing and reducing the error. And this is the model. You do the curve fit with the three parameters, the gain and the delay and the time constant. This is in the form of Kp by tau s plus 1 e power minus ds. That is the typical first order plus time delay notation in industries generally we use. So all these three parameters we estimated. Once you know the gain, delay and time constant, then you can use any kind of tuning method to tune your PID parameters. This is one use case of a dynamic model in CISO form to implement your process control solutions. Next, we see the state space model, and the innovation form of state space representation is this. As I mentioned here, from the given input output data, we need to identify the state space matrices A, B, C, D, and here you have K as well. Since it is an innovation form, this captures the disturbance. So this input, this captures the disturbance form of the plant. So ABCD captures the plant model and K encodes the disturbance part. So again, here we need to identify the order, which is typically the number of states we represent with n, and the state space matrices we need to identify. Again, the second order properties. To identify such kind of a state space model structure, so we use what are known as a subspace identification methods. To use any subspace identification methods, generally those algorithms are based on an extended form of the state space representation. So here, if we take the state space representation, so the main purpose of any model is to make predictions using the available past input and output data and also the future knowledge of the input. So that's why in state space representation, we extend these vectors, input, output vectors, in terms of past and future data matrices. Accordingly, we have the past output input data and future input and future output data. And here two parameters as a user we need to choose how much past you need to look back and how much future you need to consider. So based on these two parameters, you get what are known as the data matrices. And once we have the data matrices, then we can extend the state space model. Then you get what is known as extended state space model. If we see this extended state space model, the X is also unknown and Y of this is has C and A matrices. These two are also unknown. Or typically, if we see the state space matrices, state space representation, A, B, C, D are unknown. Here you know the U, only B and D are unknowns. These are in linear relation. in terms of unknowns. But here if we see, right, A is unknown and X is also unknown. So product of two unknowns is nonlinear. So that's why, so, but to identify the state space representation using a simpler linear least squares algorithm, either we identify A and C or the state X. Once you know either A and C or X, then this becomes linear, so that you can use linear least squares algorithm. That is computationally efficient approach to identify this model. So that's why to identify state space model using subspace algorithm, either the knowledge of this one OF, or the generally we call it the observable matrix, and or the state XK, we require to identify the entire state space representation. There are different approaches, different variants of subspace algorithms are available to identify these, and then proceed with the complete identification of state space representation using these squares. Some are based on identifying OF and some are based on identifying the states. Many are based on identifying the states. Generally, many people also prefer the second approach. They identify the states, then they estimate the ABCD together once using least squares. So you can refer the literature for various algorithms. There are numerous algorithms, numerous variants to identify the state space representation. So with this, let's consider one example. Again, here we need to identify the MIMO form of the model structure in the dynamics form. This is for implementing advanced process control. So that's where we have, if you consider init, you have multiple inputs and multiple outputs. And if you consider this data, this is actually a simulated data with realistic industrial conditions. This has all kind of various flavors. The CV4 has an integrator, and the CV5 is large delays, and DV1 is the kind of disturbance variable, but is measured. So once we measure the disturbance variable, we include that in the modeling as well. Whereas DV2 is a unmeasured and random walk kind of disturbance variable. So it's an unmeasured, so we do not have that variable data. Generally, we don't model, but we need to consider the effect of this while modeling the other variables. And this is how other observation, sampling interval and the data points. So with this, these are the step responses of identified state space model using the model structure that I showed earlier. And wherever you see null, there is no relation between MB3 and CB1. That is also required in industries where there is no relation. We are not required to identify the model. We need to indicate that there is no model between that pair of the input and output. So these step response are from the higher order models. So once we have the higher order models, we need to get the specific reduced order model form for control and optimization. For implementing advanced control, generally in typical industries, we go until the third order. Whereas for PID tuning, either use first order plus time delay or second order plus time delay kind of approximation. And once we get that kind of models, and the expectation from the user is also we need to quantify the quality of each submodel. So generally we can quantify the quality of per CV per output, but we need to quantify the particular submodel quality. Generally we need to rank them as well from rank 1 to rank 5. So for general for control, the generally user uses the rank 1 to rank 3 models. And if the particular submodel is rank 4 and rank 5, the expectation is the engineer or operator again redo the step test considering only the particular MEs by keeping the other models as ideal, and redo the step test, collect new data, and again redo the identification to try to get the better models for those problematic or pure quality submodels. So that is how the dynamic models plays an important role in implementing control and optimization solutions. The third use case of model, that is again it is required for implementing control and optimization solutions, is to build a soft sensor or inferential model that relates your input and output variables and deploy that model to continuously measure or predict those process quality or inferential process quality or property variables according to the controller frequency. So this is typically the representation between input variables or independent variables or training or target variables. Or alternative notation, you can use the generic input and output notation as per our control standards. So here The F can be, the model can be linear or non-linear, static or dynamic. It could be linear in this fashion or non-linear, a different kind of non-linears, or it can be complex non-linear relations among the variables. And as I mentioned before, measurements can be continuous, analyzer, or lab data. Typically, we have the lab data for the training variables. With the available lab data, with the available continuous input data, we need to map the corresponding sampling intervals, get the overall combined data, and then do the modeling. To identify that kind of models, the model structure generally, the most widely used model structure is the linear and static form. This we have seen earlier as well. To identify such kind of models, these are the most widely used modeling techniques in industries. The ordinary least squares, generally, it's a linear and appropriate for equal error variance in data, and weighted least squares for unequal error variances, and partial least squares for correlated input variables, and nonlinear least squares to capture the nonlinear models. Again, simpler, you can capture the simpler exponential or logarithmic kind of nonlinear relations. If you want to capture the complex relations, you need to consider the approximate linear function, which is generally difficult to get it. So if you know the data, prior knowledge, error variances, you can pick the corresponding algorithm, which are theoretically proven to be effective for such kind of scenarios. If you do not know, generally that is the case, we do not know much about the process in most of the scenarios. So the expectation is the user tries different algorithms listed here and pick the model which gives the a minimum loss function, that is minimum mean square error. So if you talk about these algorithms, it's mostly linear, and if you use nonlinear least squares, you can extend a bit to capture a simpler nonlinear relations. Some application, it may be required to capture more complex features on nonlinear relationships. So that's where in industries we adapted to the advanced modeling techniques, machine learning and deep learning. And these techniques can also be used in building the PID controller tuning models and also the models for implementing advanced process optimization solutions. But again, whatever model structure you use and whatever the algorithm you use, the current expectation from the user is you need to bring it back to the step response form with the reduced model structure. So we have to see the way to bring that. Otherwise, we have to bring completely the new control strategy. So we need to skip the MPC based control strategy. We need to come up with new control strategy like RL based control strategy, so that we can avoid such kind of approximation. Directly use machine learning and deep learning kind of model structures, generate the predictions, and based on the predictions, build design a control strategy without using the MPC based control strategy. That is how generally we have to proceed. So here to focus here, the algorithms. If we talk about the machine learning algorithms, this is how the evaluation of tree-based machine learning algorithms, especially supervised and for regression. Started with the decision trees is kind of flowchart of decisions based on certain conditions, and then bagging and random forest that selects the subsets of input random and build a collection of decision trees. The other family is boosting. This is the bagging, a kind of a training mechanism, and the boosting. Boosting and gradient boosting and XGBoost. Here the random forest and XGBoost are the ensemble based methods which are widely used, since they are known to give accurate, more better accurate results. So if you see the training mechanism, how the random forest works, right? It builds number of decision trees on random subsets of the original data, and then average the individual predictions to form the final prediction. That's why we are calling it as an ensemble model. It averages the predictions from multiple decision trees, and then the average prediction is the final predicted value. This is a kind of parallel. That's why we are calling it as bagging kind of training. If you talk about XGBoost, it's kind of a boosting algorithm, a sequential kind of approach. It builds sequence of weak decisions. It builds one decision tree and finds the model error. Then in the next iteration, it tries to modify, try to reduce that error with the modified version of the data. Then combine all individual predictions to form a final predictions. So these are the two machine learning algorithms that are generally widely used for a regression kind of model framework. When we talk about the deep learning, so the fundamental building block of any deep learning is a single neuron, so which is also called as the perceptron. Let's see how the single neuron takes inputs and predicts the output. So we define the inputs U1 to UM, and each of these input values are multiplied with their corresponding weights and then added together to get a single number. Now we take the single number and apply a nonlinear activation function. That's where the nonlinearity comes in the model structure of a deep learning algorithm, deep learning model structures. And we pass it to a nonlinear activation function, and the output of this nonlinear activation function gives the predicted output. We also have a bias here, the bias term. The bias term allows us to shift the input to the activation function either to the left or right, depending on the bias value. And mathematically, this process can be represented as follows. Take a dot product, the sum of products, the weights and the inputs, and add bias and apply nonlinearity. It will give the predicted output. So the goal here is to, if you see here, we can simplify this single neuron a bit further. You get what is known as a simplified neuron with inputs and the base, and here this encodes all via some activation function. So again, the weight dot product and add the bias and apply the nonlinear function. The goal here is to estimate the network weights, so which are similar to the parameters that we are A, B parameters we are identifying in FIR kind of or RS kind of model structure. So there we are identifying the parameters. Here we need to identify these unknowns. These are the weights. So we need to identify these weights such that it minimizes the loss function from the data. So to identify these weights, we use an optimization that is known as the stochastic gradient descent algorithm, SGD. The gradient tells us the direction to maximize the loss. So it's in a kind of a derivative. So it tells us the direction to which it maximizes that. But we need to get the lowest loss. So our goal is to minimize error, mean square error, or minimize the loss function. So we need to set opposite to the gradient direction. So we first compute the gradient and update the weight in opposite to the gradient direction. That's why the negative sign with a fraction, the eta. This is called a learning rate in machine learning or deep learning algorithms. So a slightly modified version. Here we pick a single point from the randomly sampled data, whereas here we pick a batch of data points B. Again, this is one of the parameter. As a user, we have to optimize this parameter that we call it batch size. From this batch of data points, we compute the gradient. Again, move opposite direction to the gradient direction and update the weight with a learning factor eta. So when compared to this initial approach, the modified approach gives a better estimate and is faster as well, because we are considering a batch of data points. And there is a slightly advanced version of this kind of optimization algorithm that we call it as adaptive moment estimation, simply ADAM. It is an extended version of SGD, as I mentioned, and it automatically adapts the learning rate for each weight during the training process. So let's see how we can make a full single layer neural network. This is called a single hidden layer neural network. The states in the middle are not directly observable, they are hidden. Since we have the transformation from the input to the hidden layer and hidden layer to the output, we need two sets of weight, W1 and W2. So to create a deeper neural network, just keep stacking the hidden layers on top of each other. We get what is known as a deep neural network. So let's simplify this neural network with simple hidden with a single hidden layer. So we get what is known as a simplified network. Here now the inputs and outputs are the vectors, because it is a simplified version. So we have the input vector time step k, and we feed this input to the network to get output at that particular time. So the network here, if you observe, the network processes the data in a sequential manner. At time 0, if you apply the input at time 0, the output depends on the particular input at that particular time. So it processes the data in a sequential manner at every time step, 0, 1, 2, like that. And it takes the input and produces the output at particular time step. So if you observe this kind of neural network, we do not have the relationship between the times. So we do not have any time step here that can capture the interrelations or the relations over the time. So that means the output at any time step k is simply a function of the input at that particular time step. So we can't capture the interdependencies. So this is, so that is, we need a way to relate the interdependencies or to capture the dynamical relations or the relations over the time that are typically required in process control. So we are linked here. We have for that what is known as a recurrent. So this kind of deep neural network is called a recurrent neural network. It has a cell state, is kind of memory state. So it holds the value of the previous state output and passes it to the next state. So that the output at a particular state, it not only depends on the input at particular
I have one
time.
question.
Yeah.
Sir, this hidden layer, what is the significance of it? Is the one question, and the associated question is, uh, what is that equation in a nutshell tell about and predict about? And if there are so many hidden layers, how to figure out them and find out the variables or parameters associated with it?
Yeah. So the hidden layers, if you talk about the hidden layers, right, it's about increasing the complexity of your model structure. So there are certain applications that require a plain neural network without hidden layer. If you keep only the input neurons and output node without any hidden layer, it is equivalent to your static linear regression model. You can derive that. You can derive and verify that. So if you keep the hidden layers, so that means it brings some kind of mathematical structure, some models, some additional model complexity. So if your application is simpler, a kind of linear, you do not need any hidden layers. So if you want to, it's like the different model structures, right? Like FIR and R. FIR is a simpler model structure without any past terms in the inputs. Outputs. It has only the past terms of the inputs that can capture certain kind of relations. If you need to capture some kind of better complex relations in the inputs as well, generally we bring the past terms in the output. That becomes our structure. Similarly, here, depending on our application, if you think that the simpler model structure is not sufficient to capture the complex relationships among the variables, you need to keep on stack your hidden layers until you satisfy, until you try with the different hidden layers and pick the best one. So for a regression problem, as per my experience, we go max 3 hidden layers. Okay, the regression problems are simpler problems in process control. Maybe people use as many hidden layers as required in some other applications. Maybe some may use 10 or 20 like that. But in process control application, since we have the dimension of the inferential problem to take, right? For example, the regression problem, we have max dimension, max 10 or 12, that's it, the number of input variables and the output variables if we consider. And we may have limited amount of data also. For the limited amount of data, for the limited dimension, so we require to choose a simpler model structure so that it can fit the data. Otherwise, it may overfit. If you choose complex model structure, if you add more hidden layers than required, the problem is very simpler. If you require more hidden layers, so it overfit the data. It cannot generalize a new data well. So you get a wrong predictions. And also from the available data, you need to identify weights. So many weights you have to identify. If you keep on adding the hidden layers, it will keep on increasing the number of weights to be identified.
Okay. So hidden layer is those extra parameters which will help in maximizing the probability of prediction in a better way, and given the process less variables.
Yes. So if it depends on if the problem is a complex problem, you may need to add more additional hidden layers. If the problem is simpler, you just go with the simpler model structure. Okay, so it's like if the problem is simpler regression problem, we just need simpler plain regression model structure to identify for that. We just need to identify as many parameters as number of inputs. For that problem, if you use deep learning kind of with too many hidden layers, it doesn't make sense, right? So it's like depending on your requirement, you have to choose the architecture, and within that architecture, you have to choose the number of hidden layers. It's like the number of the order in the traditional model structure. Okay.
Okay. Got it, sir. Okay.
Yeah. So if you see here in the recurrent neural network, the output at particular time step is not only function of a input at that particular time step, but also a prior state. So this output depends on both the input and also the fast memory. But we have two kind of problems in these recurrent neural networks. One is vanishing gradients, another one is exploding gradients problem. So we see what is this vanishing gradient and exploding gradient problems now. So to understand these problems, we need to understand how the the gradients generally are computed in training the neural networks. The algorithm that is known as back propagation. So that is the algorithm that generally computes the gradients in with respect to the weight space. In weight space with respect to the loss function. So the algorithm. So here this is the process of back propagation in neural networks. So we need to compute the gradient of our loss function j of w with respect to our weights. So that tells us how much small change in weight that affects the loss function. So that is, if I change the w2 a little bit, how much is my error? So our goal is to minimize the error. So accordingly, we need to move the weight by moving opposite to the gradient direction. So we apply chain rule from this loss function. So we get the gradient. If you take W1, so we need to apply the chain rule one more time. So we get, if you talk about W1, we need to apply one more time the chain rule. We get what is known as the gradient with respect to W1. I mean, some change in W1, how it impacting your loss function. So we need to repeat this process for every single weight in the network. If you have complex network, as we discussed, if you have as many hidden layers as possible, we have too many layers. Here we consider only one hidden, another hidden layer. We have too many hidden layers. So we end up computing too many repeated gradients. So as a result, if the many gradient values are greater than 1, then it's like a product, right? So exploding gradient, then if the many gradient values are greater than 1, then it leads to the what is known as exploding gradient problem. So the simple solution for this gradient problem is, exploding gradient problem is gradient clipping. So trim the bigger gradient values to scale back to the smaller gradient values. That is the generic solution. And when you have the opposite problem, the gradient values are very, very small, which can be very, very small. That is the vanishing gradient problem. So to mitigate this problem, we have three ways. One is what is choosing the activation functions. We have the activation function, as I mentioned. That's where we bring the nonlinearity. We need to choose an activation function such that it avoids the vanishing gradient problem. And initializing the weights intelligently. So the weights, we have to provide the initial guess, right? So we need to choose that appropriately so that we will not end up with the vanishing gradient problem. The robust solution is to use more complex recurrent unit that effectively track the long-term dependencies, because the vanishing gradient problem makes the model to focus on short-term dependencies. It ignores the long-term dependence that may exist because of vanishing gradient problem. So it can capture only the short-term relations. It cannot capture the longer relations, the longer dependencies. So that's why the robust solutions, we go with the complex recurrent
Sir,
neural.
I have one question.
Yeah.
This entirely everything is about error, and basically this when explaining the first one, that is U1 to JW H1 Y1, where you said W2, where we see the error and predict the something JW. That means JW output you already know to figure out the error of W2, or in what context you said the error word, and how to figure out which is the error.
No. The thing is, the error is this one. This is the gradient. So gradient tells us, as I mentioned, in which direction we have to move, so that minimizes the loss function. So once
Got it.
Yeah. So that means the gradient, how it tells, right? If some change in W2, if you make some change in W2, how it impacts your error, whether it is minimizing your error, whether it is maximizing your error. If it is maximizing your error, we will not make that change. We'll go we make some other change. That change in which direction you are moving, it's kind of some search space, right? In which direction you are moving, that tells our that is directed by our gradient. Okay.
Okay, sir. Got it.
Yeah. So the recurrent neural networks, to mitigate, as I mentioned, to mitigate that diminishing gradient problem, generally we go with the complex recurrent neural networks. That is, the recurrent neural networks with gated cells are called as LSTM, the long short-term memory neural networks, and gated recurrent unit. So these are the advanced recurrent neural networks. So those units are specially designed for capturing the long-term dependencies. So the specialty of these neural networks is they use gates selectively to add and remove the information which are relevant or irrelevant. So they have the gates which are known as forget, and so if it is the information is relevant, so they are trying to forget that, and then if it is relevant, then they store information and proceed with the next step. That is how they proceed with the training process and learn the relationships among the variables. So to demonstrate these algorithms with the traditional approaches as well, consider an inferential application where we have the input, some number of inputs here. Mostly these are temperatures and pressures. And this is our output variable, which is, I think, this is from some demethanizer column. So we need to identify mesoform of static kind of model structure here. If you want to bring the dynamics, so there are two ways to bring the dynamics. With the machine learning algorithms, you can't bring the dynamics. They are always static form. Whatever the model you are identifying the machine learning algorithms like random forest, XGBoost, they are all static model structures and they are non-parametric. So you can't write any mathematical equation between input and output based on any machine learning algorithm. So they are somehow based on some condition, some kind of training mechanism. They are trying to learn or capture the relationship between the inputs and outputs. There is no model structure. So they are non-parametric. You can't talk about any parameters there. When it comes to the deep learning, so we have a kind of model structure that has the unknown parameters, which are nothing but the weights. So our target is to estimate that weights that minimize the loss function such a way that that model form captures the relationship between the inputs and outputs. So here, as I mentioned, if you use the recurrent neural networks, if you don't use the recurrent neural networks, if you use the plain neural networks, the multi-layer perceptron or single-layer perceptron, that is single hidden layer neural network, the multiple hidden layer neural networks, they are all in a static form. Again, they are the static model structures it will do. It can capture only the static relations. If you want to explicitly handle the dynamics, you need to bring the lagged form of your input and output variables into the model structure. So you need to form the lagged form of the input and output variables. So the drawback of forming the lagged variables, right? It increases the dimension. Suppose if you have 3 inputs, if you consider lag 10, so instead of 3 inputs dimension, it will have 30 is the input dimension. So the problem dimension increases. So from the data, you need to try that much bigger dimensional problem. So we need to consider all such things while handling the dynamics with the machine learning algorithms or the plain neural network algorithms. Whereas if we talk about the recurrent neural networks, they are known to capture the dependencies over the time. That's where the time step plays a major role there. But again, you can't increase the time step too much. It increases the dimensionality of your dimensionality of your data. Again, it takes longer time to train a network. You have to limit. But depending on our process conditions, you may need to look back a longer period. Suppose your process is slow process, very slow process. It takes a longer time to reach steady state. So you have to capture those relations. So you need to bring the longer duration of lag times. It's simple, right? If you take a water bottle, if you take a bigger 20-liter can, so if you are filling the water with the water bottle, it takes very less time to fill. That means it takes very less time to reach the steady state because the inertia is very low. If you take the 20 liters of water can, if you try to fill the water, it takes longer time because the inertia is more. I mean the time constant is more. So it takes longer time to reach the steady state. I mean it takes longer time to fill it. So we need to consider accordingly. So if you are considering the 20-liter can, that is a kind of typical column in a plant, a bigger column in a plant. So if we consider the lag terms only, so let's assume we have 1 second is the sampling interval. If we consider only the last 5 seconds lag terms, like -1, -2, -3, -4, -5, within 5 seconds, you can't capture your dynamics of your 20-liter can because it takes longer time to reach the steady state. From the starting, at least you need to have the lag times to capture the steady state. That's what generally we do in FIR model structure also. So similar way, if you want to capture the dynamics sufficiently depending on the process conditions, we need to explicitly form the lag terms again with the recurrent neural networks as well. So again, as I mentioned, it increases the dimension. Again, we need to consider that as well while building deep learning based models for control. And once we build that, the other problem we need to worry, as I mentioned, if your control strategy is based on MPC based, again you need to approximate that to a reduced order step response based kind of models. So these kind of things we need to keep in mind while building these kind of models for advanced process control and optimization. So this is the output variable data snapshot. You can see somewhere the sudden spikes and somewhere the slow varying trend and somewhere the fast varying trend. So this is the typical behavior of nonlinear. And also other nonlinearity comes in terms of the operating conditions. If we see the histogram of the data, so here there is a one operating condition, here is another operating condition. This is another typical behavior of nonlinearity. Nonlinearity could be two ways, due to operating condition, different operating conditions. Another could be due to the process conditions. So we are kind of need to predict or continuously measure this output variable data to feed that to the controller so that the controller continuously take an action on the particular variable. So these are the model predictions. This is for training the training set and this is on test set. And if you see the linear model, as I mentioned, there are kind of nonlinear features in the data. So as expected, we can't expect linear models to do good job here as expected. It is not tracking the trend and you can see the difference in the actual and the predictions here. Similarly, in the test data, this is on the trained data and the test data. If you see the random forest model predictions here, I just illustrated only for the random forest here. So it is able to capture the slow and the fast features and the sudden spikes as well. So even on the test data, it is doing good. So if we compare the mean square errors of different models that we build on this data, so this is how the mean square errors. So if you see again in the mean square errors, if you see the linear model 0.01 and here 0.001. So almost 10 times better than the linear model here. So that is again, again we need to go with based on the requirement. If our requirement, our relations are simpler, could be mostly linear or a simpler non-linear, we could approximate well with the linear kind of model structure. So it is always advised to go with the linear kind of model structures and linear algorithms. If we require to capture complex, generally it happens in polymer industries or upstream. So in wells and all where you may encounter some kind of significant nonlinear features there. So in such kind of applications, so generally if required the complex model structures, then we can turn on to the machine learning or deep learning kind of model structures. So again, if you do not know any idea about the process conditions and the data, the generic approach is try all the models, check the model quality, and evaluate the model, the loss function, and pick the one which gives your better predictions or better results, and also evaluate that model on the separate different features, new data set, so that you can properly evaluate your machine learning and deep learning model if it is a machine learning and deep learning model, so that it generalizes well on the new data. Otherwise, simply deploying that model in the plant and it will not predict well means it will be a problem. At least we need to make sure it predicts the direction well. At least if the direction is opposite, then many things goes wrong in the yeah, that anyway you are aware of those things. So with this, I will summarize this session. So to give some points here, what are the major developments that will emerge in process industries in coming days or coming years, right? The advancements in production automation. So there is a lot of scope to automate the production completely with advanced analytics and artificial intelligence that can lead to more reliable and safer operations. And also the other thing is generation of meaningful insights to help operators and engineers to optimize operational performance. That's where many users expect some kind chat GPT kind of insights from some kind of analytics or tools that give some kind of guidance to the operator where things are going wrong and what kind of action he has to take to mitigate that. Such kind of things, expectations are there from the users. And as we mentioned when Rajesh pointed about that, physics informed neural network models for modeling the dynamics of the process. So if there is a scope, we need to bring the physics in terms of the model structure inside the neural networks so that it captures the dynamics of the process well. Because as you know, right, if the complexity of the model is, if we add too many hidden layers, then complexity becomes high. So we end up having too many weights. So we need to identify that many weights from the data. If we talk about the process plant, we may not have that much sufficient amount of data. We may have sometimes sufficient amount of data, but the quality may not be that good. So when you figure out the quality of the data from the large pool of data, you will end up having a small amount of data. So in such cases, if you know some physics about the process, if you bring that, then we end up having only the smaller portion of the model to be identified from the data. So that's always benefits the model quality. And the other thing that may already, so some people are tried, some people are trying now, both in the industry and academia, the reinforcement learning based advanced process control that completely eliminates the need of MPC based control. So that is one, and the other one is PID control tuning. Although there is no much scope from the business side, but people are still looking into the PID controller tuning based on reinforcement learning instead of the traditional approaches, the model-based approaches that we discussed. So these are some major developments that will emerge in process industries in coming days, and some are already in the process of doing and exploring such things. Yeah, thank you everyone for listening to this talk on this session. Although there were some glitches initially, thank you for your patience as well. These are some references. Yeah. Any questions? Then we can take up the questions.
Participants, you can.
Any questions?
Yeah.
What is meant by this physics informed neural networks? Are you giving input to the model, or you are using the physics based model for evaluating the model?
It's like if you have the process, right? If you know some part of the process.
Okay.
Suppose if you know, right, if you have some MVCV relation, if you know that the gain could be this much, so you need to bring that information into the model structure, so that the resulting model, whatever it generates the predictions, right, it generate according to the gain that you input that. It's like bringing the known information of the process. So there are in identification, right, there are three things. One is we call it as black box models. So you do not know anything about the process. You have one process, you just completely covered with a black cloth. You do not know anything about the process. You just input just exert the input and give some step input and measure the output. It's like you have the input and output data. You try to identify the model from input output data only. That is black box model. Other
Yes.
thing, complete knowledge about the process. Complete knowledge you have. Then use the basic first principles or conservative laws to arrive some kind of differential equations or partial fractional equations. That is a model, right? That any mathematical expression that represents the relationship between input and output, that is what our model. Then that is a white box model.
Yes.
There is no data. It's completely process knowledge you are deriving. And the other thing is gray box modeling. So that's where the partial. So if you know something about the process, you bring that information into your model structure and only model the remaining portion from the experimental data.
Okay.
That way the physics involved machine learning, right? The expectation is if you have some knowledge, generally know in a plant, know in a particular unit, if you consider, right, because the operator engineer spends a number of years in that plant, right, he has some understanding about the plant. So he has some relations, how the relations are happening, he has some understanding. So if you bring that understanding into the model structure, that always helps the model quality.
Okay. Okay. Thanks.
Any other questions?
Any more questions?
Okay, if no questions, then we can conclude then. Yeah, thank you everyone, and thank you Professor Nalinikant, and thank you Professor Rajesh, for giving me this opportunity.
Yeah.
Thanks a lot. Yeah.
Thank you,
Sudhakar.
Sudhakar, for a very concentrated presentation, very
Yes.
highly informative. I mean, you went into the fundamentals and forming the mathematical equation and the model equations, how we can integrate these machine learning AI into process control.
Yeah.
So it's very informative. I hope the people who are working in these control systems, they gain a lot of knowledge from your presentation.
Yeah, because having worked in the industry as an operator, so I know how Honeywell contributes to this advanced process control.
Yeah.
We normally, I mean, I should not say it now, but it was 20 years before, like when I was a fresh graduate chemical engineer, was working in alkyl benzene plant. We normally tend to avoid using any advanced process control. We generally feel that we don't have control over the process if we give it to the APC.
Yeah.
So
Yeah,
that is the
we
mentality.
from
I
many
mean,
customers also. Even if
yeah,
you
that's right.
make everything automate, right? They don't like it. If you make
They
everything
don't
automate
like it.
also, they don't like
I
it.
was at the other end. I was at that end. That's what I'm saying.
Yeah,
So I
yeah,
was on that side. So
yeah.
I can completely understand how much effort is being put in to make sure that and to optimize the process and to reduce the human error kind of thing. How
Yeah,
much
yeah.
it's beneficial.
Yeah.
So reduce the reduction of the human error is the major factor for which all the management is going towards this advanced process control kind of thing and using AI and ML for optimizing and increasing the productivity. Thanks, Sudhakar. So it's good to know about all the models like SISO and then MISO and then MISO and MIMO, and you have explained it very well with all probable models for all these three systems. It was indeed informative. Thanks a
Yeah.
lot.
Thank you, Professor.
Thank you,
Yeah.
Sudhakar. Yeah,
Sure.
have a good day. Bye.
Yeah.
Bye, good night. Yeah.
Right. So Rajesh, you have participants again. You can use the same link to provide the
Yeah,
feedback.
the link is same for the feedback.
Yeah. So
You can finish the feedback. And we are taking the
so
attendance from the MS Teams itself. I will download the attendance now.
yeah. All the slides and whatever, as soon as we receive questionnaire, whichever I said, right, will be shared with